Today we're going to take a look at Newton's law of cooling, and this will be more of an application problem involving both exponential functions and logs. So the temperature of a cooling liquid in a large room with a steady temperature is just going to be a great example of a transformed exponential function. So our first exercise here, it says consider the decreasing exponential function. Again, remember, we know it's decreasing because we can see this b value here. B value is less than 1. It's also going to be greater than 0. So we can see that it has to be a decreasing function. So it says use your calculator to sketch the graph using this window indicated. So if we go to our calculator, I've already plugged this in. A couple things that we want to take note of here. Notice your y-intercept, okay, where it's actually crossing the axis, which is at 8. Hopefully that makes sense. Y-intercept, remember, make x equal to 0 and you can solve. And remember, it's going to be asymptotic to our x-axis. So if I'm looking at this, again, just to show you how we could find that y-intercept, I would plug in 0 and I would solve for the y-intercept. Keep in mind, anything raised to the 0 power is 1, so that's where we're getting this intercept from. So somewhere over here, I would label that 8. And I know it's a decreasing function, so I know that my graph is going to go swooping down, and it's going to be asymptotic to the x-axis. So that would be a sketch of our graph. And it says, clearly, the value of y gets smaller as x gets larger. Does it ever reach 0, y, or y not? So we've looked at these functions before, and we had said no, and we could see it on the graph. It's going to continually get smaller and never reach 0. So think, if I'm ever taking this function, am I ever going to be multiplying this by 0? How would this function equal 0? I would need to take this function, and I would have to have some number in here that I would be, multiplying this function by 0. And I'm never doing that. This value here will never reach 0. No matter what I raise this exponent to, that 1/2 raised to any power, that's never going to equal 0. And we've looked at that. Even anything raised to the 0 power is always 1. We can't get this to be 0. So if I'm not multiplying it by 0, it's never going to reach 0. So not multiplying by 0, it's never going to reach 0. It will get super close. It's never going to get there. Okay, so we're going to try another one. So we are going to model a liquid's temperature that's cooling in a room. So assume a liquid starts at a temperature of 200 degrees Fahrenheit and begins to cool in a room that is a steady temperature of 70 degrees. So the room doesn't get colder or warmer than 70 degrees. So we're going to draw a rough sketch of what we think the liquid's temperature would look like as time increases. All right, so if it's cooling, I know my temperature, notice that's on our y-axis versus time. As time progresses, I'm assuming this temperature has to be decreasing. Okay, now I also want to think to myself, but we have a limit here. We have this constraint. We have a limit of 70, saying my liquid that I have can't get any cooler than 70 degrees. So I know there's got to be some sort of a line in here, maybe at 70, that my graph won't go below. I can't get a liquid in a room to be cooler than 70 degrees if the room is at 70. I know it's starting at 200. If it starts at 200, this is my initial value. And keep in mind, your initial value is going to be where x is 0. So if I know x is 0, I could say here's my y-intercept. I know it's going to be decreasing over time, but I know it's never going to get below 70. So if I have a line here at 70, it can't get below 70. So that's kind of a rough sketch. Okay, so based on our graph and our work in number 1, why would an equation in the form of a times b to the t not model this cooling? Okay, and keep in mind it says assume that B has to be between 0 and 1, kind of like we saw up above. Right? And how could we modify this equation to make it model the situation more realistically? Well, it can't model this function here, because if it did, like we saw up above, this would approach 0. And we know it's not going to approach 0 as time increases. Okay, we know it can't approach 0 as time increases because the room is at 70 degrees. So the temperature, if we're thinking about this, has to reach 70. Since that's the temperature of the room, it has to reach 70 degrees. So somehow we have to modify this equation. And if I'm thinking of this in terms of transformation, it looks like that asymptote that we had at the x-axis has been moved up by 70. So if we think about this in terms of transformations and this function up here, if we could take this function and say, well, I need the same basic function, but it has to move up 70. If I edited that equation and said, how about plus 70, that would move this equation to be a little bit more realistic. So in general, I could say A times B to the T plus C, and in this case, C would be 70 since that's the temperature of the room. That would be an equation that would model this situation a little bit better. So if I want to move things up or down, that's another situation. I would either add or subtract a variable at the end of the equation. Okay, so now we're going to try that with this situation. So we're going to stick with the same cooling liquid that we had before, the one that starts at 200 degrees Fahrenheit, and it's going to cool in a room that's held at a constant temperature of 70. So same thing that we just talked about. We're going to model this cooling Fahrenheit temperature using this equation, kind of what we had on the last example. A, B, and C are all parameters or constraints in the model, and T is time in minutes. Okay? So it's saying which of these constraints is equal to 70 and why. All right, well, we kind of talked about this already in the last problem. We know that C has to equal 70. And if I'm thinking of this in terms of transformations, if I'm going to add or subtract anything at the end of the function, that's going to be a shift up or down. So if I either add or subtract a value at the end, okay, it could be at the beginning. Okay, so maybe I'll just say add or subtract a value. We know what's going to happen is it's going to shift up or down. Okay, so if I add, I'm going up. If I subtract, I'm going down. Okay, none of these constraints is equal to 200, but it says T of 0 equals 200. So now if I think about this, let's just think like as a coordinate. So that looks like when x is 0, y is 200. Okay. What constraint does this let you solve for? Okay, so well, let's actually try it. Let's go into this function, and I'm going to plug in 0 for my t value, and then I know for my y value, that's what the y value is, right? So when I plug in 0, I know my y value is going to be 200. So let's think what we have. So 200 is equal to A times B, I'm plugging in 0, plus C. Okay, so let's solve this. So we know anything to the 0 is 1. So now I have an equation that is A times 1 plus C. But we know C is 70. We found that back here. So you know what? Let's change this to 70 so we can see what we actually have. And now look what we can solve for. Now we can solve for the value of A. So if I were to subtract over that 70, we now know A is 130. So just by knowing T of 0 equals 200, and think about what this is. This is your y-intercept. So knowing your y-intercept is going to allow you to solve for A. So in order to find the value of B, what else would we need? Because we already have A, we solved for A, we know what C is, that's our shift up or down. So in order to find B, okay, we need some additional information. So we know A and C, right? Let's get down what we know. We know A is 130. We know C is 70. We also need now another point. So at this point, now we need another point in that form of, think about it as, again, like we had up above, time, comma, temp. That's what this was up here. At time 0, I had a temperature of 200. So I need a time and a temp to plug in to that equation. So we're going to determine the value of B. That's what we're looking for. If the temperature after 5 minutes is 153 degrees Fahrenheit. So think what we said, time, comma, temp. So that gives us the coordinate, the time, so 5 minutes, comma, temp, 153. So there's our coordinate that we're looking for. Now we're going to use this formula that we had back up here. Think about that formula that we had up on the top that was in that form of f of x equals a, b, t to the c. So same kind of form. Keep in mind here is our x comma y that we have, right? X comma y. And now we're going to kind of plug it in like we did back up here in letter B. So I have a y value. I'm going to set that equal to, remember I have my a value, we found that up above. Here's a. We don't know what b is, I'm looking for b. I know the exponent here should be 5. And then remember we had that plus 70 because we had to shift it up 70. Okay, so now we need to solve. So I'm going to subtract over 70, so that gets us 83 is equal to 130 b to the 5th. And our next step would be to divide each side by 130. So this is going to get us 0.63846 is equal to b to the 5th. All right, well, if that was b squared, we would take the square root to solve for b. But since this is b to the 5th, I need to take the 5th root to solve for b. And when we take the 5th root, we can find that b is equal to 0.91417. Okay, so we found b. We found a, we found b, we know what c is. We should be able now to try and put this all together. So it says, what is the temperature of the liquid after half an hour or an hour or 2 hours? Well, we should be able to put everything together. Let's write a general equation, and then we could solve. So f of t is equal to, we need our a value, which was 130, times our b value of 0.91 raised to the t plus c. So we've just developed that equation. Now, knowing that equation, if they're saying after a half an hour, we have to think, well, what's going to happen at 30 minutes? So we could go to the calculator and plug this in. So if I were to use that equation, we'd have 130 times 0.91. Raise that to the t. Our t in this case, if it's half an hour, is 30 minutes. I'm going to arrow over and add in the 70. So at 30 minutes, I get 77.67. Okay. So 30 minutes, we get 77.677. So that would give us a coordinate if I'm thinking of this. And now we can do that for the next two, after an hour, after 2 hours. So here's a nice thing. I can arrow up and just press enter. That will just copy that in. And now the only thing I have to change on this is if it's after an hour, I want this to be 60 minutes. So at 60 minutes, I'm now down to 70.45. So notice we're getting closer to 70, but it's not quite 70. So we said 70.45. So again, here's a coordinate. Oops, sorry, this should be 60. At 60 minutes, we have about 70.45. And now after 2 hours, so 2 hours should be a total of 120 minutes. So let's see what happens. Same idea. I can go back up and I can copy. Press enter. And again, I'm going to change this now so that this is 120 minutes. And we get even closer. But notice again, this is not 70. It's 70.00158. So we could use the calculator, we could sketch the graph, and we could also kind of do this by hand, knowing what's going to happen. We know that our y-intercept is at 200. We know that it has an asymptote at 70. And we know that it's going to be decreasing just like so. Again, you could check this on your calculator, and we could label different points on our graph. Okay? So very last thing, it's saying algebraically determine to the nearest tenth of a minute when the temperature reaches 100. Okay, so we're going to go back into the formula that we found up in letter E. And if it needs to reach 100, I need to set that equation equal to 100. So we're going to use that equation. And now we're going to solve. So step number 1, we're going to subtract over the 70. So I'm going to have now 30 is equal to 130 times 0.91 to the t. Okay, next thing we want to do, remember we're solving for our exponent. We want to get everything away from this exponent. Right now it's only attached to the 0.91. So I want to get rid of that 130. And since that's being multiplied, I want to divide through by 130. So now I'm left with 0.230769 is equal to 0.91 t. Here's where logs come in. So I'm going to introduce a log to each side, because if I introduce a log over here, the rule is that exponent comes down in front, and that's what we're trying to do to solve. So now I have log of 0.230769 is equal to t log of 0.91. In order to solve for t, divide each side by log of 0.91. And what you're going to find is t is equal to about 15.5 minutes. So here's an application of when we would actually use logs, when they would be important, and what to do with them. Okay, bring any questions that you have in the class and we will go over this. Hope you guys have a great day.